So the title is Reducing the H0 Tension with Exponential Acoustic Dark Energy.
Yeah, thank you very much. Thank you for the organizer invited me to give a talk. Today, I will introduce two things. One is what is H0 tension, and the second is why the eADE model can release the H0 tension. So first of all, the discovery of Hubble constant was in 1929, almost 100 years ago. At that time, Edwin Hubble found the essential velocity of the galaxy. This V is propagated to the distance to the observer. This distance. So the constant here is the Hubble parameter. It means the expanding rate of our universe. At the beginning, the Hubble's result is around 500, and maybe 2 years later, Lemaitre also found the H0 parameter around 600. All of them have a very large error bar with better detectors. We have more and more accurate result of the H0 tension and of H0 parameter, and this is a H0 result from very early universe. It means from Planck result around redshift about 1000. They have the H0 result equal to 67. Even the BBN result, BO result, and DS result also around 67. But in the late time, it means very local universe, such as this Schultz result from supernova. They have the result for the Hubble constant around 74. That is a big difference between the early and late universe result. The tension is even larger than 4 sigma now. If we compare some other results, this tension of the Hubble parameter is larger than 6.1 sigma. That's like a big break of the bridge of our universe in the early universe or in the late time universe didn't have the similar expanding rate discovery. That's the most popular math to reduce the H0 tension in the theoretical part. The first is to add additional neutrino or additional radiation, such as this can release the H0 tension effectively, but it will change the CMB sound horizon in this math. The second math is consider a curved universe, such as we consider the universe is not flat anymore. It can release the H0 tension, but not too much effective. The third one is considering decaying relatively massive dark matter. It can release the H0 tension, but it also will change the CMB sound horizon. The last way is early dark energy. It means add additional dark energy in the very early universe, even before the CMB time, before the recombination time, such as this one. It can release the H0 tension. We will focus on this in the next part and explain why it can release the H0 tension. First of all, if we want to release the H0 tension, we should focus on the conmoving sound horizon, RS. It the distance from the hot Big Bang to the recombination time. This theta star has been observed by the Planck very well. So we just focus on the comoving distance, the chi star. The chi star is almost equal to this function. We can see if we want to get a larger value of the H0 from early observation, we should have a smaller chi star of the comoving distance. If we have a smaller chi star, we will also have a smaller RS, the solar horizon. That corresponds to a shorter history from hot Big Bang to the recombination time. Okay, that's the review of the all the solutions to release H0 tensions. They from the Arman race and Silk. In this review, they introduced kind of a early dark energy model. We will introduce the most general one, and also the acoustic dark energy. Finally, we will introduce the exponential acoustic dark energy is our work. The early dark energy model is from the two professors from Johns Hopkins University, and they have a special equation of state in the early universe for the early dark energy. At this part, they have the equation of state with a free parameter Wn. This Wn will depend, can be written by this, and n can be any other number larger than 2. But the early dark energy, the first model, also have a problem. It will change the oscillation of a damping scale. For it will change the CMB damping scale and acoustic oscillation. So the second one is a paper from Winnie Hu. They introduce another new model, the acoustic dark energy. It can release the H0 tension very well and have another equation of state. In this part, they have 2 additional free parameters. One is the WF equal to 1, and the second is P. All of the two parameters was put by hand. So we consider a new model with the exponential form of the acoustic dark energy was written by this. In this equation of state, we have less additional parameters than the previous models. And we can see the behavior of equation of state here in the very early universe, much more earlier than the time of matter and the radiation equivalent. In very early time, all of the 4 models will behave like a dark energy, but with the expanding, that at the time radiation and matter equivalent, they have different behavior in the present A equal to 1. They will change to different things. It means after this time, this additional dark energy, all of the 3 models will change and disappear in the late time universe. From the above equation of state, we can give the density evolutions. This is omega eADE that based on the two parameters. One is FC. FC is the ratio of the exponential acoustic dark energy to the total energy. And then we consider the sound speed, CS equal to 1. They have different results than the standard models. This is the pressure of the eADE model. We can see it can have an order of 3 to 1 and 0. And the sigma is can be written by this. We also calculated the perturbation for the eADE model. Two parameters can be tested in the global fitting. One is the time of AC. Second is the ratio of the early dark energy in the equivalent time. That is FC. That is the result of the early dark energy and the ADE model. We can see the FC is almost very small number. It means the additional dark energy will no more than 10% in the early universe.
We need to remember that point one, right? To get this substantial.
Totally, yeah.
Right. So it seems twice your over 0.08. Why is this so? The second number is hard. You can't underrate this.
This is one?
That number is too small, right?
Right. That. No.
So you always say instead sound speed equal to 1. So 1 means equal to the speed of light.
Right.
Okay, so then why you call this sound?
Yeah. At the beginning, we also did the fitting for the CS. It almost equal to 0.9. So for simplest the global fitting, we do the second fitting is you consider CS equal to 1. So it means we have two kind of fitting. One is CS is free parameter, it's almost equal to 1. So in the next fitting, we just fix it. Okay. This is the fitting result of eADE model. The red one is n equal to 2, and the blue one is n equal to infinity. We just select one result to compare with the ADE model. We can see the EDE model can give the result of H0 parameter around 70.3. And the second is global fitting result for ADE. The blue one is lambda CDM, and the yellow one is AED. We can see it can be distinguished with lambda CDM very well, especially it have a larger density in the early universe. And it can also release the H0 tension around 70. So the third is the fitting result of our model. It can also release the H0 tension very well. The green one is lambda CDM, and the blue one is eADE model with all the data set. We can compare the result with the EDE and ADE model, the energy density is smaller than the ADE model, but larger than the early dark energy, and the equivalent time is more later than the two model. Finally, it can also release the H0 tension very well.
Actually, the second model maybe it has an extra parameter, so like you know to EDE, because it perform much better, right? It's probably worse. EDE is the worst model. Minimum model.
Why?
It has a P parameter, right?
Right, right, right.
With EDE, you can sort of motivate, that sort of equation state for some funny, let's say, scalar potential. And it's still quite ad hoc, but at least maybe feel good with that. Very, very contrived.
Yeah, have parameter put behind, but the phenomena is also very well to compare with the observation.
But it fits better, the extra parameter, right?
Yeah.
You justify that extra parameter. Because if it's good enough to sort of say, well, E is maybe very neat.
I don't know how about the result. They didn't do this. We also compare the result with Planck data. We compare with the TT mode and EE mode data with lambda CDM and our model. The blue point is blue point from Planck 2018. And we can see our model have a very small oscillation, can be more closer to the Planck data set. Even in the EE mode, even in the EE mode, our result is more closer to the observation data. That's the conclusion of our work. First of all, we give a new dark fluid model with special exponential equation of state to release the H0 tension. And second, our model have less additional parameters, but have similar effect to release the H0 tension. The last conclusion is our model is better than lambda CDM compared with the CMB data size. That's all I want to talk. Thank you very much.
Thank you. So any questions?
Yeah, I have one question. So what about the sigma 8 tension?
Sigma 8 tension?
Yeah.
Okay. I didn't show this. It means it cannot release H0 tension.
So more or less the same result as lambda CDM.
Maybe worse than lambda CDM.
Okay, thank you.
So I have a naive question. So in your model, does your model include some violation of the null energy condition?
Violation? Maybe
So the W always greater than -1 or less than?
No, in the beginning it almost equal to -1, and with the expanding of universe, it's become positive and finally become 1. Okay, show this part. In the beginning, this may be 10% in our universe, but with developing, it more and more small. So in the present time, it almost equal to 0. Yeah.
Okay, thank you.
So you fix CS squared equals to 1.
Sorry?
You fix the sound speed equal to 1.
Right.
So why do you do that? Is there any reason, like, is it physical motivation? Because it can be anything, right? And if it goes to 0, you have clustering dark images. Right?
If it's close to 0, it's no possible close to 0 because we have do the fitting. Just we didn't show the fitting result in this slide. It almost equal to 0.9. So just for simpler for the fitting, we just select equal to 1.
But you have varied it in your analysis, and you find that the data prefers.
Right.
Any other question? Then let's thanks to speaker again.
Thank you very much.